So the Big Bang is an event when space gets very hot and very dense and filled with particles, and that may happen again.
For the purpose of this discussion, we will focus on explanations within the realm of physics. The universe did not exist forever. It came into existence approximately 13.82 billion years ago through an event known as the Big Bang, where matter, energy, space, and time originated in a fiery explosion. Over time, it expanded, leading to the formation of galaxies, including our Milky Way, which is just one of about 2 trillion galaxies. This is the Big Bang theory. But initially, the concept of the universe emerging from nothing seemed outrageous to many scientists, and they hesitated to accept it. Famous physicist Brian Cox strongly rejects the Big Bang theory and says that nothing can emerge from nothing. What's more fascinating is that the James Webb Telescope has made an astounding discovery that proves that the Big Bang wasn't the beginning of the universe. This raises the question, what occurred before the Big Bang? And if it wasn't the beginning, what was it? Before we explore that, let's consider the origins of physical matter. When it comes to explaining the creation of stable matter composed of atoms or molecules, none of it existed during the Big Bang, or for hundreds of thousands of years afterward. We possess a fairly comprehensive understanding of how the earliest atoms formed from simpler particles once conditions cooled sufficiently for the complex matter to stabilize. We also comprehend the fusion of these atoms into heavier elements within stars. However, this understanding fails to address the question of whether something emerged from nothing. Let us delve deeper into the past. The initial long-lasting particles of any kind were protons and neutrons, which constitute the atomic nucleus. They came into existence about 1/10,000th of a second after the Big Bang. Before that moment, there was no material in the conventional sense. Nonetheless, physics allows us to trace the timeline back to physical processes that precede stable matter. This leads us to the grand unified epoch, entering the domain of speculative physics, since our experiments cannot generate sufficient energy to investigate the processes of that time. However, a plausible hypothesis suggests that the physical world consists of a mixture of short-lived elementary particles, including quarks, which are the fundamental constituents of protons and neutrons. During this epoch, matter and antimatter existed in roughly equal quantities. Each matter particle, such as the quark, possesses an antimatter counterpart that is almost identical except for one distinction.
When matter and antimatter encounter each other, they annihilate, releasing a burst of energy. Consequently, these particles were constantly being created and destroyed. But how did these particles come into existence initially? Quantum field theory informs us that even a vacuum, which supposedly represents empty space-time, brims with physical activity in the form of energy fluctuations. These fluctuations can give rise to transient particles that quickly vanish. While this may appear as a peculiar mathematical concept, particles of this nature have been observed in numerous experiments. The vacuum state of space-time teems with particles continually emerging and disappearing seemingly out of nothing. However, this implies that the quantum vacuum may be something rather than nothing, despite its name. The philosopher David Albert has criticized explanations of the Big Bang that claim to derive something from nothing in this manner. If we inquire about the origin of space-time itself, we can turn back the clock to the exceedingly ancient Planck epoch. This period occurred only 1/10,000,000th of a trillionth of a second after the Big Bang, and it was during this point that space and time became subject to quantum fluctuations. Physicists typically study quantum mechanics for the small-scale world of particles and general relativity for the vast cosmic dimensions. However, to gain a complete understanding of the Planck epoch, we require a comprehensive theory that combines quantum mechanics and general relativity, known as quantum gravity. While we haven't yet developed a flawless theory of quantum gravity, there have been attempts like string theory and quantum loop gravity, which suggest that space and time are not fundamental, but rather emerge from underlying quantum processes akin to waves on an ocean's surface. Our perception of space and time is a result of these quantum processes at a microscopic level, which may not be intuitive to us as creatures residing in a macroscopic realm. During the Planck epoch, Our conventional understanding of space and time breaks down, and our reliance on cause and effect becomes unreliable. Nevertheless, all proposed theories of quantum gravity describe certain physical processes that occurred during the Planck epoch, serving as a quantum precursor to the familiar notions of space and time. However, the origin of these processes remains unanswered. Until we make further advancements toward a unified theory encompassing all aspects of physics, we cannot provide a definitive answer. Currently, the most we can confidently state is that physics has not discovered any confirmed instances of something arising from nothing. There are proposals suggesting cycles originating from nearly nothing. To truly address the question of how something could emerge from nothing, we would need to elucidate the quantum state of the entire universe at the inception of the Planck epoch. All endeavors to accomplish this remain highly speculative. Some theories resort to supernatural explanations, such as a designer or creator, while others within the realm of physics propose ideas like the multiverse, which posits an infinite number of parallel universes or cyclical models of the universe experiencing repeated birth and rebirth. Renowned physicist Roger Penrose, who was awarded the Nobel Prize in 2020, has put forward a fascinating yet controversial model called conformal cyclic cosmology to explain the nature of the universe. Penrose was intrigued by a remarkable mathematical connection between the early stage of the universe, characterized by extreme heat, density, and smallness during the Big Bang, and the future state of the universe, which is projected to be extremely cold, expanded, and devoid of matter. His radical theory proposes that these two states become mathematically identical when pushed to their limits. However, this nothingness is still a form of something. It constitutes a physical universe, albeit an empty one. The enigma lies in how the same state can be interpreted as both a cold, empty universe and a hot, dense universe, depending on the viewpoint. The answer lies in a complex mathematical technique known as conformal rescaling, which is a geometric transformation that alters the size of an object while preserving its shape.
Penrose demonstrated that the cold, empty state and the hot, dense state could be connected through such rescaling, aligning their space-time structures, although not their sizes. It is admittedly challenging to comprehend how two objects can be identical in this manner despite having different sizes. However, Penrose argues that the concept of size loses its relevance in these extreme physical conditions. In conformal cyclic cosmology, the progression of events unfolds from an old and cold state to a young and hot state. The existence of the hot, dense state is a consequence of the cold, empty state, but this causality does not follow the familiar pattern of a cause preceding its effect in time. In these extreme states, both size and time cease to hold their conventional meanings. The cold, empty state and the hot, dense state effectively occupy separate timelines. From the perspective of an observer within its own temporal framework, the cold, empty state would continue indefinitely. However, the hot, dense state it gives rise to occupies an entirely new timeline of its own. It might be helpful to perceive the hot, dense state as emerging from or being grounded in or realized by the cold, empty state in a non-causal manner. These ideas have a metaphysical character and have been extensively explored by philosophers of science, particularly in the context of quantum gravity, where conventional notions of cause and effect appear to break down. When we reach the limits of our understanding, the fields of physics and philosophy become intertwined and difficult to separate. Conformal cyclic cosmology presents speculative yet detailed explanations for the origin of our Big Bang. However, even if Penrose's ideas are supported by future advances in cosmology, they may not address a deeper philosophical question concerning the origin of physical reality itself. How did the entire system of cycles come into existence? This leads us to ponder why there is something rather than nothing, which is one of the fundamental questions of metaphysics. However, for the purpose of this discussion, we will focus on explanations within the realm of physics. There are three main possibilities when considering the origins of these cycles. Firstly, there may be no physical explanation at all. Secondly, there could be an infinite series of repeating cycles, with each cycle representing a distinct universe. The initial quantum state of each universe would be explained by some aspect of the universe that came before it. Lastly, There is the option of a single cycle and a single repeating universe, where the beginning of the cycle is explained by a feature of its own end. The latter two possibilities are appealing because they avoid the need for uncaused events. They provide a comprehensive explanation within the realm of physics. Penrose suggests a sequence of endless new cycles influenced by his interpretation of the quantum theory. In quantum mechanics, a physical system exists in multiple states simultaneously until observed, at which point it randomly collapses into a single state. Penrose proposes that each cycle is influenced by random quantum events, resulting in variations between cycles. This has promising implications for experimental physicists, as it could allow us to detect faint traces or anomalies in the radiation left over from the Big Bang, observed by the Planck satellite. Penrose and his colleagues believe they may have already identified these traces, attributing certain patterns in the Planck data to radiation from supermassive black holes in the previous universe. However, other physicists have challenged these findings, and the validity of their observations remains uncertain. The concept of endless new cycles is central to Penrose's vision, but it is possible to transform conformal cyclic cosmology from a multi-cycle form to a single-cycle form. In this alternative view, physical reality consists of a single journey from the Big Bang to a maximally empty state in the distant future, and then back to the same Big Bang, giving rise to an identical universe once again.
And to make sure you don't miss out on anything mind-blowing happening in our universe by subscribing. Thanks for watching.